Project is about permanent magnet DC motors, and my name is Micah.
I'm Parker.
And I'm Olivia. And as you can see from our diagram below, we got perm and ant magnet DC motors.
DC motors we study today, using magnets and currents. Hooray! Force creates torque, and our motor does work. We hope it makes sense, what we'll say. Permanent magnet DC motors are little electrical motors that they convert electrical energy into mechanical energy using current and magnetic fields. This mechanical energy presents itself as angular motion via torque from magnetic force. In other words, that protruding metal piece that sticks out of the motor rotates, and we can use that to change that mechanical energy into some greater form of motion. These motors are commonly used when conserving space is important because the motor is small, but controlling the motors precisely is not, because it's very difficult to control what is happening inside the motor from the outside. For instance, automobile starters, toys, wipers, washers, hot blowers, air conditioners, and computer disk drives, which were some examples from the site Electrical for You. Some of the assumptions and simplifications we made. So we're simplifying our explanation by discussing a DC motor with the most simple commutator. On the right side, we have a commutator with 6 sections, as you can see. So there'll be 6 jumps or something like that. But in the DC motor that we are describing, there's only going to be 2 sections. Typical DC motors have commutators cut up to many different sections, which speeds up the rotational motion generated. We'll talk about that later. We're also simplifying our discussion of DC motors to specifically permanent magnet DC motors, because we want to talk about magnetism, and there's actually a bunch of types of DC motors. We're also assuming we can treat the wire that helps power this DC motor as a current carrying wire.
Micah said earlier, we are going to talk about DC motors with 2 commutators. This can be seen in this picture right below, where there is current flowing through this little wire. Now, what's important about this is that, as we learned in class, current flowing through a wire produces a magnetic field. And we also know that permanent magnets produce a magnetic field. And so, using the right-hand rule, we can find the direction of the magnetic field in the wire. So, now what's special about this is that the magnetic field produced from our bar magnet points north to south, and the magnetic field produced by our wire points in the opposite direction. And so what happens is that it wants to get away from there and rotate, and it's the opposite thing on both sides. So on one side of our commutator, you have a pushing force up, and the other side is a pushing force down, and this causes our thing to rotate. And what's really cool is that once it rotates, the current direction switches, as can be seen from these little brushes hooked up to our commutator. So a magnetic field is produced by our commutator on 2 different sides of the wire, and the magnetic field is also produced by the bar magnet. And what's cool is that once this rotates, the current switches. And when the current switches, the magnetic fields produced by the wire are in the opposite directions, meaning it wants to rotate again. And this process will keep going on and on forever. Here we can see the magnetic fields keep switching directions, and so it keeps rotating forever. Now, this is only with one commutator. If we were to add more of them, we would see even more rotation, as this magnetic field would be switching even more. Olivia is going to talk a little bit more about that in our sense-making section. Lastly, to help illustrate this, we drew a diagram to kind of show what's going on here. We have the magnetic field of the bar magnet, and then as well as the DC flow of current through our battery. And it's an important thing to note here that this is DC current, but the current through our commutator is not DC. In fact, it keeps switching every time it rotates, and this is what's causing the rotation.
So here we have our magnet behind the wire, which is rotating this way. So one way to explain why the current flips as it moves is through magnetic force. So our magnetic force equation is charge times the velocity of the charge crossed with the magnetic field it's experiencing. So we know already that the magnetic field is pointed downwards, but we want to figure out how the direction of the magnetic field, of the force is changing. So when it's rotating this way, kind of into the page, like that, we know that the velocity of the top is going to be into the page. So that's our velocity. And the velocity on the bottom is going to be moving out of the page. There's the velocity on the bottom. To find the magnetic force, we just use the right-hand rule to determine the direction. So we have the velocity pointing into the page on the top and the field on the moving downwards. So that means the force is moving this way at the top. And it's going to be in the opposite direction for the bottom, but we can just double check with our right-hand rule. So going into the page for velocity, going out of the page for velocity on the bottom, field is still moving downwards, so we still have a force that is in the horizontal direction and it's moving to the right now. The force that we're talking about is on the charge that's in the wire. So the force on the charge in the wire is synonymous with the current that's moving through the wire. So when the loop is in this position, the current is going to be moving this way. So that's why as it moves around, the current has to flip to make sure that this direction is still being upheld.
We're now going to discuss the relation of PH213 concepts to the permanent magnet DC motors. And they do rely on magnetic fields from the permanent magnet. And I think there's also some from the current carrying wire. Circuitry, including that current carrying wire, and torque. The permanent magnet provides a magnetic field. Current carrying wire brings charges that interact with the magnetic field. And a combination of current and magnetic field creates torque from magnetic force that creates torque that rotates the rotor, converting electrical energy into mechanical energy. We can see where this torque comes from the equation for magnetic force on a current carrying wire. F equals current times length crossed with magnetic field. And we can use the right-hand rule to see the direction of that magnetic field as well. And here we have the actual equations that we were taught in lecture that we can relate. So the magnetic moment that points from north to south is going to be current times area vector, and the torque on the magnetic moment is mu cross magnetic field. And here we have the equation for a magnetic field through a current carrying wire. And the magnetic field from a permanent magnet, we weren't given the equation, but we do know it points from magnetic north to magnetic south.
Okay, so there are a lot of similar and different concepts that we've already explored that relate to magnetics, such as electric fields, which behave very similarly to magnetic fields, such as the whole opposites attract rule, and there being two different types of poles or charges, which is, in our case, what causes the motion of the DC motor, as Parker explained. Although there are a few key differences, like the equations and the values themselves are slightly different, and objects like magnets and current carrying wires give off magnetic fields, electric carrying or current carrying things have magnetic impacts as well. So there are a few similar things that we've explored that are similar to DC motors or helped us to reason through them. So in one of our labs, we worked to measure the magnetic field of the Earth using a compass and created a magnetic field by running current through a spool of wire. So this gave us some practice with seeing how electric fields can also have magnetic impacts. And we also got the compass to move around from this too, indicating the magnetic field that we created. And it helped us to measure magnetic fields. In homework 9, problem 2, we explored the induced current through a copper loop due to a current-carrying solenoid, and this showed how induced magnetic fields happen, or induced current can happen. We also used a magnetic induction table and magnetic force reasoning, which we're going to use in a moment to look at some sense making. And finally, in a lecture early on during our introduction to magnetics and also in the Get Ready activities, we strengthened our intuition when it comes to magnetic fields and the cross product, both of which we definitely used while exploring this problem. So, a few sense-making strategies for DC motors. We could flip the battery, which would effectively change the direction that the current is moving in, and therefore change the direction of rotation of the motor. We can also add more sections to the commutator. Adding more commutators is going to effectively increase the angular speed because there is more continuous flow throughout the DC motor and continuous change. So effectively there's more changes there's more turns or current changes, and this is going to increase the velocity. And also, if we use a stronger permanent magnet, this would strengthen the torque, because the torque equation for magnetic fields has the magnetic field in it. So increasing the field by increasing the strength of the magnet would increase the magnetic torque. And we also have our torque equation from 212, where we looked at net torque is equal to moment of inertia times angular acceleration. And so from there we can see that increasing the torque would increase the angular acceleration, which increases the angular velocity and gives us a faster spinning motor. And here are our sources.
We hope you liked what you were shown, and we hope that your knowledge has grown. Magnets are fun! Let's skip into the sun. Together we'll face the unknown.